Hi, my name is Kara,
Hi, I'm Luke.
Hi, I'm Lucia.
and for our project, we decided to create a hydroflight problem that utilizes topics from exam 2. So the learning objectives for the hydroflight problem is to apply Bernoulli's equation to determine the power required of pumps and to perform a momentum balance. So this is a diagram of what we use to create this problem. The pump is actually located within the jet ski, and the jet ski forces water under pressure into the boots that are located within the flyboard. And from there, the boots use the jet nozzles to provide thrust to lift the person up into the air. Just a little background, the creator of the flyboard, his name is Frankie Zapata. He's a French inventor. He invented the flyboard in August of 2012. And currently the flyboard is used for both water sports and Pilates. But Frankie invented the flyboard because he was born colorblind, unfortunately. And his dream was to fly in both helicopters and planes, but because he's colorblind, he can't. So instead, he uses the flyboard to fly over water and also over land with just air. Currently, though, the flyboard is being used in water sports and Pilates, and the industry for water sports generates about $43.2 billion a year worldwide. And in America, 13.6% of Americans participate in water sports every year. So clearly, this is a very profitable market.
So based on what we learned about hydroflight, we decided to design our problem around this. So as mentioned before, hydroflight can be achieved by pumping water to something like a flyboard or a jetpack and then expelling that water through a nozzle at a relatively high velocity. So with this in mind, we decided that assuming that both the hose and the jetpack nozzle used both have a diameter of 8 inches, what would be the minimum velocity of water required to lift a 180-pound person? We can do this with the momentum balance. Then from there, using the velocity that we just calculated in part A, we can actually calculate the pump head required to lift a person 30 feet into the air if we assume that the water does not lose velocity after it is ejected from the jetpack nozzle. Now, with the pump head calculated from Bernoulli's equation, we can actually solve for the horsepower needed to be provided to allow the person to maintain the flight. This horsepower comes from the jet ski that is connected to the hydroflight hose. And lastly, we can use the horsepower calculated versus the weight of the person to decide how much horsepower is needed for each weight of person. So for part A, assuming that both the hose and the jetpack have a diameter of 8 inches, we know that the pressure at the hose entrance and at the nozzle are both atmospheric, that V in is equal to negative V out, that the force provided by the person is equal to the mass of the person times gravity. Then, using a momentum balance as shown on the right, we can plug in our numbers and actually come up with that a velocity of 11.52 feet per second is required to lift the person.
Next, we wanted to use this velocity to calculate the pump head required. So for this part, we made the assumptions that the pressure at the jet ski and at the jetpack cancel, that the velocity of the water down at the jet ski is negligible, and we used a friction head of 15 feet to account for losses through the hose. And once you set up your Bernoulli equation in head form and plug in these assumptions, it turns into a plug and chug problem where you get a pump head of 47.07 feet. Next, we wanted to calculate the power. So for this, we use the pump head and gravity to get work, and then we use the density of the water, the velocity, and the area of the hose to figure out the mass flow rate. Then we just multiplied these to get a power of 21.5 horsepower. Next, we wanted to plot the weight of the person riding the jetpack versus the power supplied by the pump. So here on the x-axis, we have the weight, and then on the y-axis, we have the power. And you can see, obviously, for a lighter person, it requires less power. This graph actually gives us an insight to the safety constraints for the jetpack, because you can see when a person who weighs less than 50 pounds uses it, it would be pretty dangerous because the power at that point becomes uncontrollable.